Hi everyone. Today in our final project, we're going to talk about how to spend every dollar. So given the budget, as in the price ranges from commodities, it matters to us how to spend all the budget. So here we're going through a brief introduction of the project. And for the background give we have limited resources and time, and how to make better use of resources of time is always a hot topic. This topic is very relevant to us. And in this project setting, we will simulate a situation in which certain resources are given and multiple tasks need to be done. The person should distribute resources into tasks and ensure to fully utilize the resource. Given an analogy, although in real life it's not likely to be in a situation where we need to use as much money as possible, but we can see the money as the resources we have. So as the backpack problem, we need to choose items we want to carry with us so that the backpack is left with limited space. So for the problem to solve, our project is to solve a question to spend every cent of the budget, given the budget as n, and we have different items from C1, C2, C3 to CK, and for each item I, the commodity CI, the prices range from BI to TI. You can choose from different price within them, and our target is to spend every cent of the budget. Okay, and now we give a very simple example. For example, if we have a budget in as $26 and we have a one commodity, it's called C1, and the price range of C1 is from $5 to $10. So in this situation, the best solution that we buy 5 pieces of C1 at the price of 5. In this case, we have $1 left. Okay, this is the brief introduction. So now we're going to listen to more analysis about the project.
Analysis and algorithm. For this question, we can use dynamic programming because this question can be divided into some sub-problems. If we can solve these problems, we can get the answer of the original one. And we can use dynamic programming in this problem. If we want to spend K dollars, we can first solve the amount less than K. And usually we would like to pruning first when we deal with those problems by dynamic programming. For most of the cases, we can just use one type of commodity to spend all money. We can first consider a commodity whose minimum value is min and maximum value is max. Then for X dollars, if this equation exists, then it must be possible to spend just about all of the X because satisfying min times X over min and smaller or equal than X and also X smaller or equal than max times X over min. It's just possible for find a new point such that which satisfy the X equals to this new point times X over min. And for those square brackets that are or downwards rounding operations. So from this part, we can derive a new conclusion that if X is bigger than some value from these mathematics skills, and we can make sure that this kind of amount of money, we can use all of them. And so if the money is higher than this threshold, then it must be possible to spend all the money by just one kind of commodity. So we can find the minimum value of all of the threshold, which can be calculated by each kind of commodities of its min value and max value. And further optimization of pruning is done later in the sample and proof steps. And step 2 is the dynamic programming pre-processing, and studied dynamic programming part, and where DPI denotes the maximum amount of money to be used if there's an I. Currently, this problem is a deformation of the complete backpack problem. Different goods may appear in the interval of overlapping prices. So in fact, the main consists for a special amount of K, and there's not a commodity that can have exactly K dollars cases. So here we use the array visit I to indicate whether there's a single item with price I in prices records the price that can be reached for each individual item. And for step 3, then the dynamic programming status transfer, and we use two loops, and the outer loops enumerates all the prices can be achieved for single commodity, and which can be interpreted as corresponding to each of the different commodities in the complete backpack problem. And while the inner loop recurs from the current prices I to the amount of C for DP, because at this point a new price commodity like prices I is introduced, which can be derived from DP and J minus prices I. So here's the equation we can use to get the final answer. DPJ equals to the maximum of DPJ and prices J plus DPJ minus prices I. So the answer is the total amount of money minus DP and total amount of money.
Okay, cool. Let's discuss about the complexity and also give some example based on the whole algorithm. So as it is introduced for the whole algorithm, we know there are 3 steps to solve this question. So for this first step, we are going to find if there is a special case that we can only purchase one commodity to spend all the budget. Let's say if the budget is 30 and we got 2 commodities. The commodity 1 with price range from 11 to 16 and commodity 2 with price from 17 to 18. So based on this equation, we can find that it satisfies this equation. So we know for commodity 1, we can, with only purchasing commodity 1, we can spend all the budget. Let's see if that's correct or not. So if we purchase C1 with 14 and another C1 with 16, 14 plus 16, we spend all the budget. And also if we buy 2 C1s with price 15, we can also spend all the budget. So cool. But however, if it's the same budget, we have the same budget, but for the price range of the commodity 1 is different. Let's say if it's from 11 to 14, it now cannot satisfy with this equation. So we can find by only purchasing 1, the maximum number of money that we can spend is 14 plus 14 is 28. We cannot spend all the budget. Also for C2, we cannot spend all the budget. So if we can no longer just purchase only one type of the commodity to spend all the budget, we need to go to the step 2. Before that, let's discuss about the complexity of this step. So the time complexity for this step is just OM, and space complexity is O1 because we didn't create any data, and where M is the number of the commodities. Okay, so for the next step, we are going to integrate the prices. Let's say the former example, that C1 we had price from 11 to 14. So finally we will have this price array with those numbers from 11 to 14 and from 70 to 18. So for this step, the time complexity is OM and the space complexity is OM times R, where M is the number of commodities and R is the largest range of the price of the commodity. There is a space complexity because we create this price array, and because we need to iterate through all the commodities, we got the time complexity as OM. Okay, so based on the information we got from step 1 and step 2, we can finally reach the final step. We are going to use dynamic programming to solve this question. So remember that we got this equation. We will know that dPr equals to this thing. Before that, we create a dP with size 30. which is shown as the following table. We got 0 to 30. So I omit this from 1 to 9 because we cannot buy any of the commodity with this amount because we cannot afford these commodities. So from 11 we can just buy this commodity with price 11. For 12 we can buy 12, and also for 13 and 14. But for 15 we can see that we can buy this commodity. We can buy this commodity with price 11. Then we have price, this is 11, and DP 15 minus 11, we got DP4. However, our DP4 is 0, so we have 11. We put 11 here for the 15. Then we check the price is 2. Price is 12. And by the same logic, we will update this DP15 with 12, then 13, then 14, and 14 is the maximum for the DP15. Also, follow this same logic, we can fill this table until 30, and finally we can find this 30 that we can spend all the budget. So for this step, the time complexity is all m times n, where m is the number of the commodities and n is the budget. And the space complexity is all n, because we need to create a dp in terms of the size of the in terms of the amount of the budget.
So I will talk about the limitations and the future avenues of our approach. After completing this project in a short period of time, although each of us are satisfied with the result we have achieved, but there are still some weaknesses and limitations which provide us some thoughts about the future avenues. We provide a method for users to know how much budget they have left based on a given budget, and with an unlimited number of goods with the prices within a given range. However, the users do not know how to combine these items to achieve their goal. So to improve this, we can add data structures to keep track of the goods combinations. And also the algorithm we provided is based on integer values, but in reality, the prices can be false. This method allows users to know the minimum amounts of money they can have left without worrying about to maximizing their total net income. But what if each commodity has different net income and the users want to spend as much money as possible while maximizing their total net income? This is also a direction we should explore in depth. So even though our algorithm provides users with the answer, we can improve user experience by including user interface that allow users to input different commodities and budgets in different price ranges instead of just opening the code editor to run the original code. So in conclusion, we have defined a project problem, which is determining if the user can use as much resources as possible with certain limitation on the given choices. Introduced the method we produced to solve this problem, went through examples of the algorithm, and analyzed the time complexity and space complexity, and list out some limitations and future avenues of our approach. Thank you for your listening.